The first derivative of a function can tell us about extreme values, or at least local extreme values, of the original function. The second derivative can tell us about concavity. But we might not even know what concavity means. Maybe in your physics class you've talked about convex and concave lenses. So just know that a function is concave up when it looks like a smile or a cup. And a function is concave down in places where it looks like a frown or like an umbrella. This is not very scientific. We're going to get to the science, the calculus, that can tell us for sure where a function is concave up or concave down. But just so you can start to get a feel for when looking at a graph, is it concave up or concave down? So a parabola whose leading coefficient is positive is concave up everywhere. A parabola whose leading coefficient is negative is concave down everywhere. The function y equals e to the x, concave up everywhere. The function y equals natural log of x, concave down everywhere. And the function y equals square root of x, concave down everywhere. But a function like sine of x changes concavity. This part is concave down, this part's concave down, this part's concave down, but these other parts are concave up. So, oh, here, I'll show you this other example. Supergiant fun example. So pause the video for a second and see if you can tell which parts of this graph are concave up and which parts are concave down. So I say this graph is concave up from about here to about here, and from about here to about here. And this graph is concave down from here to here, here to here, here to here. So we'll get more practice at that. Just start to get to use that idea of concavity. All right, so we said the second derivative can tell us about concavity. A function is going to be concave up anywhere where the second derivative is positive. A function is concave down anywhere the second derivative of the original function is negative. And then just by definition, that place, that one point on a graph where a function changes from being concave up to concave down, that point right there, it's called a point of inflection. But the interesting calculus thing, the way we find that point of inflection, a point of inflection is a place where f double prime changes sign. Now, probably one of the second or third most common error on the AP Calculus test is people thinking that a point of inflection occurs anytime that f double prime is 0. But it's more specific than that. Just like just having a critical point doesn't guarantee we have a relative extreme value, just having f double prime equal to 0 doesn't guarantee a point of inflection. A function has a point of inflection when its second derivative changes sign. So make sure you write that into your nose paper, and then also there's a place for it on your green paper. So there's an example on your paper. Find all the points of inflection of the graph of y equals e to the negative x squared. Well, to find a point of inflection for a function y, I'm going to have to find where y double prime changes sign. So my first job is to find y prime. Y prime. Now you can see why we spent all that time in chapter 3 taking derivatives. Because in chapter 4 we're going to spend most of our time taking derivatives and then using the result to answer a question. So this is going to be e to the negative x squared times the derivative of the exponent, which is negative 2x, which I might write as negative 2x e to the negative x squared. Normally I wouldn't care so much to rewrite my work, but if I'm going to have to take the second derivative, I want this sort of be as clean as possible. That's a multiplication there, so when I take the second derivative, I'm going to have to use the product rule. Y double prime is going to equal the first times the derivative of the second plus the second times the derivative of the first There we go. And I'm looking for where the second derivative changes sign. That means I'm going to have to figure out where the second derivative is positive and where it's negative. So just to clarify, that was an equal sign there. All those exponents on the x's are 2's. So my best bet here is to factor. Let me rewrite this once a little bit. It's going to equal negative 2x times negative 2x is negative 4x squared times e to the negative. Oops, negative times negative, positive 4x squared e to the negative x squared minus 2e to the negative x squared. My next best bet is to factor. I'm going to have to set that derivative equal to 0. So that's going to be e to the negative x squared times 4x squared minus 2. I'm going to write that up top so I want to set that second derivative equal to 0. So 0 is going to equal e to the negative 2. So two things multiply together to equal 0. One of the two things had to be 0. The thing about e to the negative x squared is that can never equal 0. Doesn't matter what exponent you put onto a positive number, the result's never going to be 0. So that meant 4x squared minus 2 had to equal 0. 4x squared minus 2 had to equal 0. There's a couple ways to go about this. You might like to factor out a 4, I think is the fastest way. That makes x squared minus a half equals 0. And this you can actually factor as a difference of squares, even though probably in your Algebra 1 class you were told this wasn't a difference of squares, because 1/2 isn't a perfect square. This is x minus the square root of 1/2 is 1 over square root of 2. And x plus 1 over square root of 2. It means I'm going to make a number line. I'm going to mark negative 1 over radical 2. Now maybe you saw 1 over radical 2 and you wanted me to put a petal on the flower because you said, Mrs. Hicks, you left a radical in the denominator. Don't tell the pre-calculus class. But nobody cares in calculus if you leave a radical in your denominator. So feel free to leave that as 1 over radical 2. You could have rationalized it to radical 2 over 2. They're both equivalent. Here my other 0 is 1 over radical 2. Now I'm going to go through that process where I'm going to check a point. This is f prime. Sorry, this is y double prime. So I'm going to check values into y double prime, and you'll find that I get positive values when I plug in numbers less than negative 1 over radical 2. I get negative numbers when I plug in 0, for example, and I get positive values when I plug in numbers that are greater than 1 over square root of 2. So I would conclude that y has points of inflection in two places. At x equals positive or negative 1 over square root of 2, because I ran out of room here. So I'm going to bump up to the top, because y double prime changes sign at those values.